Hello, y'all. Welcome to lesson 92 of my DP chemistry curriculum. Today we're going over reactivity 2.3.6. This is an HL topic. In this topic, we are covering the equilibrium law, which is the basis for quantifying the composition of an equilibrium mixture. We will solve problems involving values of K and initial equilibrium concentrations of the components of an equilibrium mixture. So we're going to be looking at different equilibrium equations and quantifying what is in the beginning and end of the equilibrium. So we're going to look at it in three different ways. The first way we're going to look at it is look at initial and equilibrium concentrations to determine the equilibrium constant Kc. This is one very common type of problem that you might find in the DP curriculum. So this entire video is just going to be examples and solving them. So in this problem, we might get two nitrogen dioxides or nitrogen monoxide gases plus two hydrogen gas reacts in equilibrium to form nitrogen gas plus 2H2O, also a gas. So we can be given initial values for moles, and we'll just say 0.100, we'll say 0.0500, and we will say zero nitrogen. We're starting with none whatsoever. And lastly, 0.100. These are all mole values. And within this chamber, so we'll say that maybe we have a 1.00 decimeter cubed reaction vessel. So one thing that we can then tell after we let this go to completion, so let's just say we put all these gases in a chamber and say, go, react. Well, eventually at completion, so at equilibrium, which I'll just abbreviate EQM. So at equilibrium, we find that we have 0.0620 mole of NO present. Using this value, we are going to determine Kc for the reaction, our equilibrium constant for the reaction. So we have a couple really important pieces of information here. We have our initial values. We have our final values for one of our reactants. Now, this presents us with an opportunity. We can now use what we call an ICE table. So we can use an ICE, which is an abbreviation, table. ICE stands for initial, change, and equilibrium. So when I create an ICE table, what I generally try and do is make a box. Oops. We'll just get this set up here. And you should eventually start being able to make these on your own pretty quickly. Now, in our box, we put our reactants and products as our headers. So we are going to start with 2NO, and I'm going to tell you it's very important to keep your coefficients 2H2, N2, and H2O. So we are now setting up our table. The last thing to note is all values in this table are concentrations, meaning mole, decimeter, cube, inverse. Now, for our problem, this is very easy because everything is within 1 decimeter cubed. All of our mole values are coincidentally our concentration values because any of these divided by 1 still gives us the same value. So we're going to go ahead and load up our table with our initial concentration value, 0.100, 0.0500, 0, and 0.100. We also know that at equilibrium, we have 0.0620. So what we're going to do is start inferring what has happened. To get from equilibrium, for our nitrogen monoxide to get to equilibrium, it has changed by losing 0.0380 moles. Because our hydrogen has the same coefficient, it has also lost 0.0380 moles. Oops, missed a coefficient for water. And because our water has the same coefficient, it has gained 0.0380 moles. But what you'll notice is our nitrogen has a different coefficient. It has a coefficient of 1. For every 2 moles this changes, this only changes 1 mole. So this will actually be a positive 0.0190 moles. So basically what I'm saying is nitrogen changes half as much as hydrogen, nitrogen monoxide, or water. Now that we have these values, we can fill out the rest of our table. For our equilibrium concentration of hydrogen, this is just math, 0.050 subtracted will become 0.0120 moles per decimeter cubed. Nitrogen will be 0.0190 and water will be 0.138. Now, I'm trying to keep track of my significant figures here, so I do not have a 0 at the end. Now, I have my equilibrium values and I can plug them into my Kc equation, which says the concentration of H2O squared, concentration of N2, divided by the concentration of NO squared times the concentration of H2 squared. And these are all at equilibrium. So just plugging my values in, 0.138 squared, 0.0190. I should drop a 0 in there. 0.0620, and that will be squared 0.0120, and that will be squared as well. Plug all this in, and we get a value of 654 for our Kc. So that is our equilibrium constant for this equation based on our equilibrium values. So this is an ice table, how we use it, and this is how we can determine Kc. This is one of the simpler examples. We're going to now move on to a slightly more challenging concept. In this one, we will calculate equilibrium values from Kc and initial values. Initial values or concentrations of reactants. So in this example, we'll take the reaction of carbon monoxide plus water reacts to form hydrogen gas plus CO2. So these are all gases here. And what we'll say is that we're going to start with 1 mole of each of our reactants. 1 mole. And normally in the DP exam, you'll have many more sig figs. So we'll say 1.00 mole of each. And we put them in a reaction vessel. We have 0 moles of hydrogen, 0 moles of CO2, and we have a starting Kc value, or we have a Kc value of 10.0 at a given temperature of 693 Kelvin. So, assuming, once again, a 1.00 decimeter cubed reaction vessel, and this isn't always an assumption. This is something that I'm providing for this problem. Sometimes you'll get a different value that you may have to then change your entire calculation for. But just to keep things simple, a 1 decimeter cube reaction vessel will create our ice table. So once again, we are only going to use concentration values here. And we have carbon monoxide, water, hydrogen gas, and carbon dioxide. We're starting with 1 divided by 1, which is 1.00. Again, 1.00. Starting with 0, starting with 0. Now, this becomes a little more difficult. We do not know what the equilibrium amount is, and we don't know what the change is. So in this case, we use variables. We'll say we lose X. If we lose X carbon monoxide, we'll also lose X water because they're in a 1-to-1 ratio. We will gain X hydrogen and we will gain X CO2, again, because it's all 1-to-1 ratio. So we have 1 minus X, and I'm going to drop significant figures for the moment. 1 minus X, X, and X. Now we can just use our Kc equation, which will give us the concentration of X, concentration X divided by 1 minus X times 1 minus X. We can simplify this to X squared divided by 1 minus X squared. Now, we know our Kc value is given as, as 10, and that is now equal to X squared over 1 minus X squared. And so the first thing I'm going to do is get rid of that pesky square. So I'm going to square root everything to find that we have approximately 3.16 is equal to X squared, or sorry, is equal to X divided by 1 minus X. To keep some room here, I'm just going to say 1 minus X is equal to, or sorry, 1 minus X times 3.16 is equal to X. So we'll simplify it further to get 3.16 is equal to 4.16x. Our x value is now 0.760. So we just did a little bit of algebra, solved for x, and now we know our concentrations. Our actual equilibrium concentrations for our products are 0.760, 0.760, and 1 minus x, 1 minus 7.760 is 0.240 and 0.240. So just like that, we've used a bit of algebra to solve for our equilibrium concentrations. That is another possible problem. The last type of problem we're going to go over is what if your Kc value is a little weird? So what if we have a Kc value that is far, all looks a little wonky, I'll just start over. 1 Kc is far less than 1, a number so incredibly small. Now, 1 Kc is far less than 1. We know the reaction shifts towards reactants. And it shifts towards reactants so heavily that we can actually make an assumption. So when it's that far less, we can assume that the concentration of reactants initially is equal to the concentration of reactants at equilibrium. I'll explain this one a little bit further once we finish this problem, but let's do a practice of it. In this case, we have bromine gas plus chlorine gas reacts in equilibrium to form 2 bromine chloride, also gas. Furthermore, I'm going to give us the Kc value, which is 8.0 times 10 to the minus 9th. So an incredibly small Kc. Given our initial values of a 0.40 mole and 0.40 mole and 0 mole, and we are now given a 0.50 decimeter cubed reaction vessel, we will find concentration of BrCl. That is our goal here. So the way we'll do it is once again set up our ice table. create our space for our reactants. Whoops, start with bromine, start with chlorine, and 2BrCl. Keeping coefficients, once again, is very important. We know we start with 0 BrCl. Now, in this case, we do not have a 1 decimeter cube reaction vessel, so we're going to have to find our concentration. 0.4 divided by 0.5 gives us a 0.80 and 0.80 mole per decimeter cubed concentration. So in this case, we have to account for the fact that our reaction vessel is not an even value. All right, from there, we know that we are losing x, and gaining 2x. Now, we said that we can make this assumption right here. The reactants initial is equal to the reactants at equilibrium, so we're just going to go ahead and do it. 0.80 and 0.80 moles per decimeter cubed. Our products, however, 0 plus 2x is still 2x. So we're going to go ahead and solve for our equation. Our Kc is equal to 2x squared divided by 0.80 times 0.80. We can see that we're already solving a problem pretty similar to the last one, as well as kind of the other ones we've done, but we'll simplify this further to 4x squared divided by 0.64. And we know that that is equal to our Kc of 8.0 times 10 to the minus ninth. So now we're just solving this equation for x. So we will continue that down here. Solving for x, we find that 4x squared is equal to 5.12 times 10 to the minus ninth, where dividing by 4 and square rooting, we get x is equal to 3.57 times 10 to the minus fifth. That's our concentration that we will then plug into our x value up there. So we know our concentration of BrCl at equilibrium is equal to 2x, which is equal to 2 times 3.57 times 10 to the minus fifth, which is equal to 7.2, accounting for sig figs, times 10 to the minus fifth. And this is the concentration, so mole, decimeter, cube inverse. There we go, that's our answer. Now, we're going to go back real quick, back to our equilibrium values. 0.80 minus x does not equal 0.80, but we made the assumption it does. Let's figure out why. 0.80 minus our x value, which we found to be this, and we'll start using some real numbers and non-scientific notation. 0.80 minus 0.1234357. When we do this math, we actually find that our value on our significant figures order is still equal to 0.80. Because if you put this in a calculator, what we're actually getting is 0.7999643. As far as we know, when doing significant figure math with addition and subtraction, we're going to be cutting off after the hundredths place, meaning we're going to be cutting off here, which when we round, we just get the exact same answer. So this is why when you have a Kc value so small, even though we're producing some products, we're not actually producing enough to shift the reactants to a meaningful change in concentration. So we can make that assumption. Anyways, I hope this helps you learn a little bit about ice tables, and have a great